Your math power this week deals with the Ulam spiral. Stanislaw Ulam was a semi-famous mathematician who contributed a unique way to represent the natural numbers. Getting bored in a math presentation, much like you are now, he began doodling on his notepad. He began organizing the natural counting numbers in a spiral, just like this. And he labeled each box with one of the natural numbers, and round he went. Mr. Wink, are you telling me that all you have to do to become a famous mathematician is just organize the numbers in a weird way like this? Yep, that's exactly what I'm telling you. And we probably shouldn't say stop here. Let's change that to pause, because the Ulam spiral theoretically will go on forever, round and round. Actually, Ulam was already pretty well respected, having worked on the atomic bomb at Los Alamos. Like many mathematicians of that time, that was a good paying job. He's also considered to be one of the fathers of the hydrogen bomb, which is 1,000 times stronger than the atomic bomb. He and Edward Teller came up with the design. I think it was actually Ulam's idea to put a charge not only outside to implode the nuclear material, but also to put a charge inside so it would explode and implode at the same time. They're both the parents of the hydrogen bomb. Nice kid you got there, just a little temperamental. Anyway, back to the Ulam spiral. This wouldn't be much on its own, but it's what he did next that makes this image unique and very popular. He began shading in the prime numbers. So you remember a prime number is a number that's divisible only by 1 in itself. Sometimes when you get a big number, like let's say 39, is 39 prime? No, because the digits add up to 12, and since 3 goes into 12, 3 goes into 39, so I'm going to skip that one. Now, mathematicians have been looking for patterns in the primes for thousands of years, and just haven't found anything, because they're pretty much randomly scattered, it looks like. But as Ulam started to shade in the prime, he noticed some things. It might be kind of hard for you to see, since this spiral only goes up to about 200. So let me show you a larger spiral. This one goes up to about 1,000. You see any patterns developing? It looks like all the primes are falling on these diagonal lines. Now this spiral has thousands of numbers on it, and then you can really see the diagonal lines that these prime numbers are forming. But I gotta be honest, I'm not so impressed with the diagonal lines. I'm more impressed with the horizontal and vertical lines, because there's a good reason for the diagonal lines being there. So what I've done here is I've highlighted all the even numbers yellow, so that you can see that it's just amazing fact that all the even numbers lie on these diagonals, which means all the odds also lie on diagonals. And if you know anything about prime numbers, you know that all of them are odd, except for 2. 2 is the only exception. But it makes sense that all the primes would fall on these diagonals, because that's where the odd numbers are. So yeah, this is interesting. But I'm kind of surprised that this is the only thing people ever talk about, the Ulam spiral, that the primes are on diagonals, because there's so much cooler stuff about the Ulam spiral that I'm going to show you that people just don't ever investigate or talk about, at least until now. So one of the more interesting things, if you're a middle school teacher like myself, is the orientation of the perfect squares on the Ulam spiral. Perfect squares are used throughout algebra and geometry. They're a really important number in those subjects. So what we're going to do is look at the odd perfect squares. 1 squared is 1, so I'll highlight that box. 3 squared is 9. That's right here. The next one's 5 squared, 7 squared. And you can see all the perfect squares are falling along this diagonal. And then if we do the even perfect squares on the other side here, we get 4, 16, 36. They're all going off in the other direction. It's almost a straight line, but it's got this little hitch in the middle here. But other than that, it would be a perfectly straight diagonal line. So you may wonder, why are these numbers called perfect squares? Well, because if you have just one shaded, you can make a square. Obviously, that's a square. But you can't make a square with 2 or 3 squares. But if you have 4, you can make a square again. And then the next perfect square would, of course, be 9. And then the next one, 16. And you see how they get their names. 25 is the next perfect square, 36, etc. And it just goes round and round. So that's pretty cool. But that is just the tip of this iceberg, believe me. So after seeing the perfect squares line up as they do, I asked myself, what else involves perfect squares? Pythagorean triples. So you recall the Pythagorean theorem that the sum of the squares of the legs equals the hypotenuse squared. Remember, a squared plus b squared equals c squared. And most of you know a few Pythagorean triples. Like I've asked you to remember the 3, 4, 5. And every multiple of that, of course, is a triple. But the 3, 4, 5 family, I asked you to remember that. And the 5, 12, 13. We're getting into trig soon, so you really need to know those. At least those two. But there's a whole bunch of them. 8, 15, 17, you're probably not going to remember. 7 squared plus 24 squared equals 25 squared. That's another family. But what I want to focus on for the moment is the heads of these families. The most simplified version of each one of these families of triples. They're called primitive Pythagorean triples. So here's a list of primitive Pythagorean triples. And there are formulas for finding these primitive Pythagorean triples, which I'm not really going to delve into here. But you can see the formulas at the top of the last 3 columns there. You just select values of m and n and follow 3 simple rules. M has to be bigger than n, and m and n can have no common factors. This means if m is even, n must be odd, or they would share a factor of 2. This is also why m equals 6 and n equals 3 is not on this list, because they would both be divisible by 3. And you don't see m equals 9 or n equals 6 on the list, or m equals 10 or n equals 5 on the list, etc., because it would be breaking rule number 2. And then the final rule is if m is odd, then n must be even. So during winter break, I made this huge list of Pythagorean triples. Actually, somebody else did. I just Googled it, but I could have if I wanted to. So I thought I would plot the hypotenuses of these primitive triples on the Ulam spiral to see what it would look like. And what a shock. So why not plot the legs? I don't know. They just seem kind of arbitrary to me. My intuition told me that the hypotenuses would be more interesting. Intuition is what makes us human and separates us from computers that just calculate. Computers can't play or imagine, or think about, well, what'll happen if I combine this with that? This is one of the themes I watched on a video over break called Dangerous Knowledge by David Malone. It's a great video. We're going to watch it, and it talks about why some mathematicians go crazy or commit suicide. It seems to have happened to a lot of mathematicians in history. So remember everything in moderation, guys, even your math. Remember that. Anyway, I digress. But I'm trying to mix up your math with a little bit of humor so you don't go crazy. So back to the Ulam spiral, I began highlighting all the hypotenuses of these Pythagorean triples. And as I went through my list, I noticed some of them repeated, like 65 was 33 squared plus 56 squared, but it was also 16 squared plus 63 squared. So I double boxed that one, and I hit a bunch of those that were double boxed. And I just went round and round until I saw this pattern. So you see any patterns? Throughout this process, I made 3 different size Ulam spirals. This is the smallest one I made. It only goes up to about 200, so you probably don't see much. So I made a bigger one that approaches 1,000. Now, you might want to pause the video here and write down what you see, because I have made 5 conjectures based on what I saw. And it would be fun to see if your conjectures match my conjectures. Okay, so here's conjecture number 1. The hypotenuse lengths of the primitive Pythagorean triples lie only in every 4th diagonal. I'm highlighting the 4th diagonals here, so you can see what I mean by a 4th diagonal. Now, I did a little bit of research, and I think these 4th diagonals are called mod 4 numbers. but I'm not quite sure. I do notice that all these numbers in the fourth diagonals are 4 apart from each other, and that's what a mod 4 number is. It's when you're counting by 4s, basically. So why must Pythagorean triples be 4 apart from each other, or some multiple of 4 apart? Answer this question and you will prove conjecture number 1. So, conjecture number 2. Every prime number in the fourth diagonal of an Ulam spiral is a Pythagorean triple. Now, this one seems much harder to prove. Are these numbers in the fourth diagonal special? I mean, we know they're all odd, and they're 4 apart from each other, or some multiple of 4 apart. But why would all the primes in this class always make the hypotenuse of a primitive Pythagorean triple? If you're interested, you can look up Fermat's 4n plus 1 theorem, which was first proven by Leonhard Euler in 1747, about 100 years after Fermat first discovered it. This conjecture has already been proven, but what's so impressive to me is that these guys recognize this relationship between some primes and the Pythagorean triples without ever seeing an Ulam spiral. So conjecture number 3, I probably could have combined with conjecture number 2 to say that every prime in the fourth diagonal makes a unique Pythagorean triple, but I decided to separate it because it sounds more impressive to have 5 conjectures than 4 conjectures. Plus, conjecture 3 is also sort of related to conjecture 4. Yeah, conjecture 3 is pretty simple. No prime in the fourth diagonal is a Pythagorean triple in more than one way. If you look at all the primes, they're only boxed once, and no more than once. So to see conjecture number 4, I had to make a larger Ulam spiral. This one approaches 2700. I'll do the diagonal so you can kind of find the fourth diagonals there. Conjecture number 4 says that every composite triple is a triple in more than one way. Maybe 2 times, maybe 4 times. There are 3 numbers here that occurred 4 times. 1105, 1885, and 2465 all occurred 4 times. In other words, these are all the ways that you could make 1105 in a Pythagorean triple. Could a triple work 6 ways or 8 ways? I don't know. I'd have to make a larger spiral, and I'm not going to go down that road. So I noticed there were some exceptions to my conjecture number 4. You notice 25 is only boxed once. Same with 169. All the odd perfect squares, they're only boxed once, which means they're composite numbers because you see no primes in that list, that diagonal list there. But they only work in a Pythagorean triple one way. Similarly, I found 5 cubed to be an exception, and 13 cubed is only boxed once. So I made the exception that for perfect numbers, you're only going to find one way to do it, and I think it has to do with the limited number of factors they have. So the last conjecture is probably going to be the hardest to prove. There exist rays of primitive Pythagorean triples that are continuous, with no gaps, along a fourth diagonal in one direction and begin at a vertex. You see one here. It's completely filled with Pythagorean triples, and one going off in the opposite direction. And then there's another one here, and another one here, and they all begin at vertices of the spiral. In other words, the corners of the spiral is where they start. But isn't that bizarre? And how are you going to prove that those are continuous and go on forever? I'm only looking at a small portion of it here. They could stop. I don't know. But that's what a conjecture is. It's something that we think is true, and you need to prove it true. Isn't number theory interesting and weird? Fermat lived long before Ulam, but incredibly he noticed some of these patterns existed without ever seeing an Ulam spiral. I'm just so fascinated by that. He also had another famous conjecture, that no triples would exist for a cubed plus b cubed equals c cubed. But it wouldn't be proven until 400 years later by Andrew Wiles, Sir Andrew Wiles. Wiles proved this a few years after I started teaching, and I can't understand his proof, I'll be honest with you, but I can marvel at what it must have taken to do it, at what must have gone into it. I'm still waiting for my autographed picture of Andrew Wiles, by the way. He is my hero, as you know, and many of my students in the past have tried to get him to break, but maybe one of you will be successful, I don't know. So in a few weeks, when we watch the story of Andrew Wiles in The Proof, the video called The Proof, please remember the Ulam spiral and what all these Pythagorean triples look like in 2D space. And try to imagine, what would a 3D spiral look like? I mean, a three-dimensional spiral, where would all the numbers go? Or how about a 4D spiral? Because that's just as impossible, I mean, whatever that is. And you can see how this is impossible, but proving it is a whole other thing.